Thanks for coming, guys. And I know I'm the one standing between you and the brick, so I'll try to be quick. Stop me anywhere you want, but I'll try to run through these slides. I'm trying to do a 2-hour presentation in 30 minutes, so you're not going to get any of it anyway. Just pay attention for a little bit. So Crossbow, what we're going to talk about is that what happens when you bring virtualization into picture, what happens to security, and how the virtual machines, when they talk on network, can compromise that, and what is there to help it out, right? So in Open Solaris, at least, we introduced a new networking stack. This is about 7-8 years of work. It's called Project Crossbow. It's an internal code name, although you can Google it, and you'll see it. What we do as part of this new networking stack is that virtualization, security, QoS, hardware isolation, all these things are designed in, right? I mean, it's a ground-up design. Took us 7 or 8 years to accomplish compared to any other OSs, including Solaris 9 out there, Solaris 10 out there, where the stack has not been modified for a long time. Let's see if we can get. So the big part of this thing is when you're virtualizing things, what we have done is taken the MAC layer, which is kind of, anyway. So all this space is basically where your MAC layer is, and this is where we have done a lot of the virtualization along with security isolation and dealing with things. So one of the things that you guys probably know, if you look at the NICs today, right, the NICs have become very advanced. Gone are the days when you have 1 gig NICs, packet comes in, shoves it in the system, and it's done. These days, the NICs have hardware classification built in, multiple receive ring, transmit rings built in, multiple DMA channels built in, a lot of security features built in, and so on and so forth, right? So what we do is, the first thing we did, we redid how the device driver is done on the system today. So in Open Solaris, the device driver does not do a lot of work. It's a very simple device driver. It's a new framework. It registers with the stack, exposes to the stack how many ring groups it has, what kind of classification capabilities it has, what kind of security features it has, and so on and so forth, right? And it's up to the stack to manage it and assign things. So this is kind of what happens. Take pre-Crossbow world. I wish I had bought my full slide deck and I could have shown you the comparative pictures. But imagine a pre-Crossbow world where packets come into the system, right? You don't know who the packet is for, right? Typically, the packet is coming in. The NIC raises an interrupt. You DMA the packet into the system memory. At that point, you start looking at the header to figure out, does the packet belong to this gentleman here or this gentleman here, right? It's already in the system, right? The packet is already inside. Now, at that point, you are trying to do various things, which is like, where does it need to go? Where is it trying to go out? And so on and so forth, right? Typically, what happens is there are a lot of risk involved in that space because it's all software. Software classification, software-based paths, and all those kind of things do tend to get bugs and so on and so forth. And also, you know, the various kind of DDoS attacks can come into picture where one virtual machine sharing the system with another virtual machine starts sending it packets that it's not supposed to send, right? Or can somehow get hold of the packets it's not supposed to see, right? So what Crossbow does is it actually takes the physical NIC, takes the NIC hardware classifier, programs it based on per virtual machine, right? So typically the idea is that you have a MAC address that's associated with the virtual machine. You program the classifier so that packets for a particular virtual machines are separated on the NIC itself. A receive ring and transmit ring and a DMA channel is associated with the virtual machine itself. So in this particular case, if you look here, this is a part of the NIC hardware that belongs to a virtual machine. Then on top of that, what you do is you take the kernel thread, kernel queues, including the CPUs that are assigned to that virtual machine or that type of traffic, and you attach them together and you create something called a hardware lane, basically. The idea of a hardware lane is that once a packet is slotted into this hardware lane, it cannot escape anywhere. All the threads that are going to process it are also tied to the same CPU. And it is done all the way from NIC hardware, right? So there's no system software involved. There's no, I mean, the system software is programming the NIC, right? But it's at the end of the day hardware itself which is separating the packet stream out, right? And that allows us to give these hardware-based lanes, which belongs to virtual machines, zones, or even type of traffic, and so on and so forth. The other interesting thing we do after that is that in terms of pure performance, when packets are slotted into a hardware lane, we do not deal with interrupts all the time, right? Interrupts are enabled only till you can keep up with them. The moment any of these hardware lanes starts lagging behind, we switch into a polling mode, right? Now, it's kind of interesting that you see in your CS 101 class, this is a long time back, we all went to school some time back, hopefully, right? Where they teach you that interrupts is kind of like an exceptional situation and so on and so forth, and you should enable an interrupt when an exceptional situation happens. So for the life of me, I could not understand why in the world of networking we still use interrupts all the time, right? I mean, these 1 gig, 10 gig NICs are building in multi-million packets per second. The NIC is designed to build a packet, bring a packet into the system. Why do you need to raise an interrupt every time you get a new packet, basically, right? So raise an interrupt only if there's no processing going on. So that's what we've done. On a per hardware lane basis, an interrupt is raised only if there was nothing happening, you got a packet, so instead of doing busy polling, just raise an interrupt. But the moment we get an interrupt and more than 1 or 2 packets, we switch into a polling mode immediately. At that point, instead of 1 packet coming into the system at a time, we are doing packet chains. See, hardware has already classified the packet. I know all the packets that landed in the middle lane belong to this virtual machine. The MAC address has already been verified, right? There's nothing else for me to do. I take the entire chain of packets that arrived and bring it all the way into the system, probably doing zero copy optimization on the way and get it into the virtual machine without anyone else seeing it, without anyone else having a look at it, right? Any questions here? This is kind of the crux of what it is. There's a question. Busy polling doesn't help, right? If you don't have load. So the question was, why don't we do polling all the time? The polling all the time because you're also running other things on the CPU, pretty much your applications and so on and so forth. So if I have a thread running all the time looking for packets which are not arriving, it doesn't work, right? So if you have no work to do and there's nothing queued in the NIC for you, just switch into an interrupt mode. At that time, when the first packet arrived, that point you can go back into polling mode. And believe it or not, we switch between interrupt and polling a couple of 100 times per second on an individual lane basis. Any other question? Okay, so this is kind of the crux of this thing. The idea of the stack is that, deal with the NIC hardware efficiently, try to separate the traffic out early, right? Do interrupt and polling, switch between interrupt and polling to be more efficient. And this also allows us to scale, right? So I didn't mention the basic thing. If you're not doing any virtualization, this is how we scale across large number of systems, right? Because you don't need to program the classifier based on MAC address. You can just program the classifier as packets are coming in based on a hash of source IP or, full 5 tuple. You can slot it into one of the lanes, and then they operate independently from each other. The other thing that I must point out, that between these hardware lanes, there is no shared counters, there are no shared mutexes, there's nothing shared at all. Even the receive and transmit descriptors are per hardware lane. There's nothing shared, right? This allows us to get 100% scaling or pre-linear scaling when we are just in the pure performance mode. Or this allows us to do virtualization at zero cost, basically, right? I mean, you're doing more separation than virtualization, but that's what people call virtualization these days. So once you have these things, the uses are pretty interesting, right? You can not do any virtualization if you're dealing with just services, right? You're a single system, you're dealing with voice over IP versus, say, HTTPS and so on and so forth. You can create these lanes, program the hardware classifier, and you can create these lanes and assign these things to the lane independently, right? Now at this point, voice over IP packets are running independent from HTTPS packets, right? And they are not stepping on each other. Voice over IP needs better latency, faster response versus HTTPS doesn't, so this works out pretty well. There's a question.
When you refer to the stepping on each other, I think you're talking about packet collision?
No, and when I say stepping on each other, a very simple case, HTTPS might be bringing in on a 10 gig NIC, 9 gig per second, right? Versus voice over IP is only 100 megabit per second stream. There's only a few packets, but they need a quick response, right? So in a typical system, what ends up happening is that there are 50 or 100 packets of HTTPS queued ahead of you. It's all FIFO, right? Pre-Crossbow, everything was first in, first out. So you have to process the 100 packets of HTTPS before you can get to that voice over IP packet, right? Not in the world of Crossbow. There are 2 lanes now, right? So voice over IP packet is all by itself in 1 lane. You process it as soon as you get it, basically, right? So this is how, now the other interesting thing we have done is we made sure that, because every NIC vendor has these features, but they program different registers, they programmed it differently, and so on and so forth. So as a user, as a system administrator, we try to hide people from all these things. By the way, I'm on slide number 6 right now. So we hide people from these details. What we do is we have a common administrative interface to programming these things, and how the hardware gets programmed underneath is our problem, not the system administrator's problem. So you are, at this point, NIC independent. You don't care whether it's an Intel NIC or Broadcom NIC or a Sun NIC running underneath you. You just utter these commands at the bottom, like flow ADM, create flow. And in this particular example, we are creating a HTTPS-based flow with a max bandwidth of 500 megabit per second, right? And that's it. You're done, right? You don't care what hardware you're running on. Currently, the things that you can assign for each flow is bandwidth limits, guarantees, priorities, and number of CPUs, right? The interesting part is that fairness automatically comes on this architecture. You do not enable fairness. The dynamic polling automatically comes with this architecture. You don't enable and disable it. That we'll always do. Coming back to the virtualization side of the house, Solaris containers, for instance, basically, you have containers with the exclusive stack. You create a VNIC with dedicated hardware lanes. You can assign them link speed. So one container is 100 megabit per second, the other is 200 megabit per second, and so on and so forth. And they have NIC hardware and a path all to themselves, right? You can, at that point, see real-time usage of each container. What are the traffic? So we will be hosting a demo in the demo booth on Crossbow. So please come by tomorrow and day after, and you will see that. All these things running in live mode, where you can see the real bandwidth usage for each of these virtual machines, virtual NICs. The other interesting part is because our counters are also on per VNIC or per hardware lane basis, we can show you history without much overheads, right? Because all we do is there's a daemon running every 15 seconds or 20 seconds or whatever. It just takes the counters and dumps them in a log file. So if you want to go back yesterday between 2 and 2:30 p.m., what was happening on my system, you can actually see the histories, right? So the log files and logging and auditing becomes a lot easier, basically. What are the virtual NICs? They're functionally similar to physical NIC. In fact, in the world of Crossbow, the physical NIC is nothing but a virtual NIC with a specific name, right? So things that you were used to dealing with, E1000G0, BGE0, and whatever, we preserve that. But all that is a name, nothing else. It's one partition of the NIC, right? Similarly, you create virtual NICs, they take other partitions, and so on and so forth, right? It's all standard-based, right? So all our virtualization stuff is based on open standards, standard VLAN. So the interesting part is you can create these VNICs on top of link aggregation. You can aggregate 2 physical NICs and create the VNIC on top and assign that VNIC to a virtual machine. At that point, the virtual machine automatically got network failover. It doesn't need to deal with it, right? And the way you create aggregation is 802.3AD, LACP, all standard stuff, right? There's nothing proprietary, there's nothing, you don't need to learn new stuff here, basically, right? The other interesting part is the VNICs are visible on the network as physical NICs. They have their SNMP MIBs attached to them. If you have configured a bandwidth limit on these VNIC, it appears as the IF speed for that VNIC. And typically your standard SNMP tools will be able to discover these, manage these, and do whatever necessary, right? And then, if you want to build your virtual private network, we have virtual switching capability in-house. You can create a virtual switch and build your virtual private network in the machine itself. Yes, I think I have an example further ahead. I'll show it to you.
So given that the names are just really historical now,
Yes.
any reason why you continue to use them? Is it just
People
rather than going, say, the Linux route and you start off and they're all called ETH, they're 0, 1,
So we have that, so thanks for pointing that out, Darren. We have that facility also. If you don't want to call things BG0, you can call them ETH0 or Net0, whatever you feel like. We have that also. We have vanity naming. But by default, we still continue the same model. If it's BG0, we call it BG0. Darren is asking why, and it's like no particular reason.
It's a massive compatibility problem.
See, there's your customer saying right there, don't do it. Let me skip a couple of slides and get to the, sure, we can have this conversation over the break. It would be interesting. I suspect we'll need alcohol to have this conversation, but that's a different story. Again, creating these things, VNix and all is pretty straightforward. DLADN, new command. I think it came in one of the Solaris updates. It got enhanced quite a bit now. So you can create VNIC. You can specify the MAC address, you can specify the bandwidth, you can specify the CPUs, you can specify the properties in one command, and done, right? Same way you can create your virtual switch, like vSwitch1, and you can create your VNix on top of that and assign them to virtual machine, and so on and so forth, right? You can modify any of these properties anytime dynamically without tearing down the thing and recreating it, right? I know people get pissed off if they have to change something and everything need to stop, right? Good. In case of global zone, the switching is taking place in the global zone when you're using zones, basically, for zone-to-zone communication. But from external communication, the NIC itself is doing it, basically, for you. Yeah, totally. So the question was, can IP filter be applied to, because everything is pretty standard base and proper layering is followed, so you can bring IP filter in to filter between the zones and so on and so on. Yes, that was the old shared stack zones kind of in between. Yes, all those things are, well, we still have shared stack zones, but the exclusive stack zones offer you a lot more if you want that kind of isolation. Yeah, yeah. Sorry? Pretty much. The overheads we provide are very small, basically, right? The thing is, at least when you're doing things on top of vSwitch, there is a little bit of overhead. We need to look at the packet. But what we measured, it's less than few percent, basically. When you're doing outbound stuff, there's no overhead at all, basically. The NIC itself is doing it for us. In fact, performance actually improves because we do dynamic polling also and packet chaining also, so it actually improves performance. There was another question.
I'm only asking you to ask this now so I don't forget.
Sure.
Crossbow in production on both PG and Intel's.
Sure.
We get duplicate packets when we use an aggregate data link.
Okay.
Have you encountered that?
There are a bunch of aggregation bugs that we encountered which are getting fixed in the current release of Crossbow, actually. So don't go away. Just remind me what bugs you are seeing if you've not filed it, because the one, I think it's a Jan or Feb release of Crossbow will have a lot of work on Agar done on it. Right, so there were some other things left in Agar. We have fixed those.
So, am I hearing this correct? That this is actually coming out in Solaris 10, or is this an open Solaris?
Right now, it's an open Solaris. Again, whether it's going to be in Solaris 10 or open Solaris is going to be Solaris Next and all requires a lot of alcohol. I'm happy to have that discussion after dinner, as long as we have something to drink and not kill each other, right? Yes, we should do that. Scotch Puff tomorrow or Thursday evening. Discussion on, let's not go there. I will probably get fired pretty soon and escorted out of the building here. So this is the case of full-fledged virtual machines, basically, what they do. So if you have full-fledged virtual machines, again, even Zen-style virtualization, we can take part of the NIC, part of Crossbow technology, and map it directly into a guest itself to get rid of the overhead. This is work in progress. This has not been achieved yet. Today, if you use Zen with Crossbow, everything goes through the hypervisor. We have a VNIC that for each guest in the hypervisor, brings its own overheads, but there's work going on to make this happen, basically. Like we said, it all works over 10 gigabit Ethernet. It also works over InfiniBand. So people who are using InfiniBand, you can create your virtual NICs on top of IB and so HPAs and so on and so forth. And everything is transparent to you, basically. The last interesting part is, I'm on slide 14. The talk about virtual private networks, basically, or building a network in the box and what it buys you, right? So the interesting part about Crossbow Virtual Network is this example was created at a customer site where I was out there giving a talk, and some of the Sun teams were trying to debug it. And then later in the evening, they asked me, hey, can you help? You're supposedly the guy who created all this mess, so can you help us debug this, right? So I recreated the same setup they were trying to debug on my laptop, right, including the link speed. The link speed was very important because that was the cause of the bug. They were totally on a 1 gig switch, but one of the machine was actually on a 100 megabit link, right? And the client there and host one, when they were talking after a long time, they would actually drop a packet, right? And few packets drop will keep in, but the problem was they were running a UDP-based system where they didn't want to see those packet drops. So we replicated the entire thing using zones and Ether in virtual switch and whatever, including the link speed, right? And we ran the same app that they were running on the server and the client, basically, right? And then we set dtrace probe points to cache the code points where it will actually do that. After running the workload for over an hour and a half, we actually got the trace we were looking for, right? And found the bug. So the interesting part is that this is kind of cool stuff, you know, you can do on your laptop. You can try for experimentation purposes. You can, because at this point, you know, I mean, I don't know how many people are still using the NS2 simulator from Berkeley and so on and so forth, right? If you're a hardcore programmer and you're trying to do protocol design, yes, that works very well. But if you are trying to figure out how your app is going to perform in a wide area network environment, we have a plugin for wide area network also. So you can plug that in the picture here. And it can specify latency jitters and packet drops and so on and so forth. And you can get a feel of how your app behaves actually in a wide area environment. Go ahead.
Yeah, we used to have to do that with a separate machine.
These days it's all networking without a wire.
Wow.
So on that note, oh yeah, how much time do I have? Minus 2 minutes. We'll skip this. Who cares about any of this? Slides are up there, guys. You can read it.
Sunay, when is your Lisa talk?
The Lisa talk should be Thursday afternoon. So yeah, I forgot to mention we have a paper on Lisa. That's part of the reason why I'm here. So that's Thursday afternoon. We'll be doing a short talk. We'll also be hosting the demo booth, and we're thinking about doing a BOF as well. So actually, a quick question. Are people interested in doing a BOF and discussing this more in details and various kind of things? I see it not. Okay, so maybe Wednesday or Thursday evening we'll host BOF and get some whiskey bottles, and we'll have some interesting conversations. Thank you, guys. And on that note, I'm right outside.
Thanks, Sunay.